Hi guys, I'm Nazmul Hassan, and the topic of today's short talk will be very extensive. I'll cover multiple topics together. I'll begin with RCS, and then I'll talk about the monostatic and bistatic RCS, and then move on to the topic of antenna RCS, which is a bit different from normal RCS. I'll talk about the structural mode antenna RCS and then antenna mode RCS. And after that, I'll talk about the plane wave, which is the thing that we use in order to measure RCS. And then I'll talk about the polarization of plane wave, which is very important. Without the concept of polarization, we cannot understand RCS properly. And then I'll talk about the theta-polarized and phi-polarized plane wave. So that would be the content of theoretical part of this video, and then I'll move on to practical demonstration in CST microwave studio software. I'll use theta-polarized and phi-polarized plane waves to find out the monostatic RCS of a patch antenna. And I will use a reference paper and compare our simulation results with the reference paper. So that would be quite fun, so enjoy this video and stick with me. So the RCS application is primarily found in military style technology. It's because most of the military aircraft wants to penetrate the enemy area without being detected. For example, if it gets detected, then easily it will be destroyed by anti-aircraft missiles. So military technology primarily uses this radar cross-section, and apart from military, we also use in aviation technology. So it's a very important field in radar engineering and antenna engineering. And basically the definition of RCS is dependent on several factors. For example, if we have a target located from the radar at a distance of r, then we can express the RCS of the target by using this equation. And RCS is primarily measured in terms of squared meters, or in more conventional unit, which is known as dBA squared meter. And it's basically the ratio of the backscattered power density to the incident power density on the target. And backscattered power means the reflected power from the target to the radar receiver antenna. And RCS depends on several factors. Primarily, it depends on the physical geometry and material, and then the direction of the radar, and then polarization of the scattered signal and signal frequency as well. The value of RCS basically is a measure of how easily detectable an object is. So the lower is the value of RCS, the better for military vehicle or the missiles or the aircrafts, because they don't want to get detected. And RCS has two classification. One is monostatic RCS, where transmitter and the receiver antenna are located at the same place. So this is the monostatic RCS. And then we have got the bistatic RCS, where we have several receiver antennas located at different positions. And we have also a transmitter antenna located at different positions. So this is the case of bistatic RCS. Now, the monostatic RCS of antenna is kind of different from the normal RCS concept. For example, if we have a planar patch antenna or any antenna, then we can define the monostatic RCS of antenna in terms of two components. The first one is the structural mode RCS, which is normally expressed by sigma s. The second one is the antenna mode RCS, which is defined by sigma A. Basically, structural mode RCS depends on the antenna type, geometry, and also the material constitutes, whereas the antenna mode depends on the reflection coefficient, basically the impedance matching of the antenna. And the total monostatic RCS of the antenna can be expressed by a single equation, a closed form equation, which is this, and where the phi is the phase difference between the two modes. Practically, all the antennas that we operate or that we employ in practical application, they are matched with 50 ohm. So they have got matched load termination conditions. So in that case, we can ignore the antenna mode RCS. And what practically matters is the structural mode RCS. But remember that if we vary the load, obviously the antenna mode RCS will come into play. So I'd like to recommend two good textbooks for a radar cross-section. The first one is Radar Cross-Section by E.G. Knott, and the second one is a classic textbook by George T. Rack, and it has got 2 volumes. So give them a try, they're a very good textbook. So then I'll move on to the topic of plane wave. We all know this topic, plane wave, and this plane wave originates from the solution of this wave equation that can be derived from Maxwell's equations. So the plane wave is one of the solutions of this wave equation. There are many solutions of this wave equation, and one of them is the plane wave solution. And why they are called plane wave? So there is a reason that they are called plane wave, because if we draw a Cartesian two-dimensional coordinate system, and if we assume the direction of the propagation of the wave is along the z-axis, then the wavefront of the plane wave will look kind of like this. They will be similar to planes. And if we visualize the moving wave in this way, then observe the orientation of the E field and H field. They are located in the same plane. So that is why we call them plane wave, because the E field and H field are orthogonal and they are located on the same plane. That's the reason we call them plane wave. So it's very important because we use this in order to find out the RCS of objects. And then we have the concept of polarization of the plane wave. Basically, this is the direction of the electric field of the plane wave, which is propagating in space and time. For example, for the first case, if we observe the orientation of the E field and H field, then the E field is oscillating along x-axis. It's pretty clear, right? So in this sense, we call that the plane wave is polarized along x-axis, because E field is oscillating along the x-axis. So it's basically a vertically polarized plane wave. And in the second case, look at the orientation of the E field. Now the E field is oscillating along y-axis. So in this sense, we call that plane wave is basically polarized along y-axis, or horizontally polarized plane wave. So this is for the Cartesian coordinate system. And we also have spherical coordinate system where we use 3 other different vectors in order to indicate the 3 axes. So imagine a point, and then we can express the 3 components of the unit vector along these directions, theta, phi, and r. And then we can obviously define the plane wave in terms of theta-polarized and phi-polarized plane wave. So for this case, observe the electric field direction. If we assume the electric field is along this direction, then we can call it theta-polarized plane wave, because the E field lies in the theta plane. All right. So it's basically the field. We observe the field orientation in which plane it lies. And in this case, E field is along this direction, and it lies in the phi plane. So we call it phi-polarized plane wave. So let's consider the first case where we have got a theta-polarized plane wave with an incident angle of theta equals 0 and phi equals 0. Then the plane wave is marked by the red color, will be like this, and the E field is in this direction, and k is the propagation vector, it's the direction of the propagation. So if we zoom this area, we can find out that k is making an angle of 0 degree with the normal incidence of the patch antenna. So this is the first case, and then the second case where we have an incidence angle of theta equals 60 degree and phi equals 0 degree. And then the plane wave will be like this. You can see the k vector and E vector. And obviously we can compare this figure with the spherical coordinate system, and then we can easily find out that the k vector, which is the violet color line, is making an angle of 60 degree with the normal incidence of the patch. Alright. So we will consider the last case, which is case 3. In this case, we will consider a phi-polarized plane wave with an incidence angle of theta equals 15 and phi equals 0 degree. So the direction of E field is along this way, which lies in the phi plane. And if we zoom this configuration of the orientation of the field, we find out the k vector is making an angle of 15 degree with the normal incidence of the patch. So we will verify our knowledge with reference paper. We will find out the simulation results in CST and then verify or compare our results with the reference paper. So this is the reference paper that I will follow. It's published in MOTL, and it's basically a patch antenna where the authors tried to reduce the RCS of a patch antenna. And they use this FSS instead of a ground plane to reduce the RCS of the patch antenna. And this is the reference antenna they used. I will use this antenna as well. Okay. And these are the figures. These are the RCS of the reference antenna. It's marked by this dotted red line curve. So I will simulate in CST and verify or compare the results with this. So I will use 3 cases. The first case is this, and the second case is theta equals 60 degree and phi equals 0 degree. And then the third case I will compare is this plot. It is for phi-polarized plane wave with an incidence angle of theta equals 15 degree and phi equals 0 degree. So in total, I will compare 3 results with this reference paper. So 3 simulations in CST, and then compare those 3 results in reference paper. So let's create a new template in CST. and select time domain, and the minimum frequency is 3 and the maximum is 13. Okay, so first of all we'll create the substrate. So let's name it substrate, and along the x-axis let's define the length, SL by 2, and along y-axis let's define the width, and this is the thickness of the substrate. Well, the dimension or the substrate they have used in the reference paper is this, with a tangent loss of 0.009 and 62 mil thickness, and this is the dimension of the substrate they used in the reference paper. I will follow exactly same specifications. Type Roger 5. So I'm searching for Roger 5880 because it has the similar specifications. You can see that. So it's 64.62 and the width is same, 64.62. Oops. Okay. So the height of the substrate is 1.55 millimeter. And then let's make the ground plane. Okay, this will be our ground plane. Let's name it ground. So SL by 2 and SL by 2, SW by 2. And this will be the thickness of the copper layer MT. And the material should be PSC. Well, MT is 0.035 millimeter. It's basically the thickness of 1 ounce copper layer on PCB board. So that is the ground plane, and now let's make a patch. So let's name it patch. Along U axis we'll define the length of the patch, and along the V axis let's define the width of the patch, and that would be MT. Well, the length of the patch in the reference paper is 15.3 and the width is 21 millimeter. Okay, so the value is 15.3 and width is 21. Okay, alright, now we completed the geometry of our patch antenna. Okay, and now let's check the field monitor. We will define the far field in broadband with the samples of 200. Okay, and now what else? Let's check the plane wave. Since we are simulating the first case, is the theta-polarized plane wave. So you can see the alpha value is 0. 0 is for the theta-polarized, and theta is the incidence angle value, 0, and phi is also 0. So this will be the first case from the reference paper. This case, okay, it's a theta-polarized plane wave. So let's go to post-processing. And make sure you selected the far field antenna properties and far field. And then from here, Monostatic RCS for parameterized plane wave. And select 1D Cartesian from here. And select the broadband far field. And we will define the step size as 0.1. And make sure that we define that theta equals 0 and phi equals 0. Okay, this is the first case. And uncheck this option because we need in dB scale. Okay, and make sure you select this unit, RCS in squared meters unit. All right. Now you are good to go. Let's save this file as case 1, theta-polarized. So the incidence angle is theta equals 0, phi equals 0, so I am using 0_0, just for convenience. Alright, now we will simulate this setup. Make sure the accuracy level is -40 dB. And you should use the source type as plane wave because we are using this plane wave to measure the RCS of this patch antenna. We haven't defined any port because we are assuming that this is this antenna has a masked termination load condition, and in that sense we can ignore the antenna mode RCS and only concentrate on the structural mode. Okay, so the simulation will continue, and you can see the simulation is running. Well, I will pause the simulation and come back when the simulation is complete. Alright, the simulation is complete here, and there is one error. Don't panic, this is a very simple error, we can fix it. This is nothing actually. So go to results templates and go to settings. The error occurred because we didn't tell CST which results to use in processing template. Now we have selected it. Now we will evaluate it, and there will be no error at all. Okay. Now the post-processing will continue to calculate the RCS at those frequency points, and I will pause the video and come back when it's done. Alright, now the RCS calculation is done. So we have got this curve. This is a curve between RCS and frequency. You can see the curve is for the first case where the theta and phi equals 0. Alright, you can see phi equals 0 and theta equals 0. This is the first case, the incidence angle. And we'll compare this plot with our reference paper plot. So let's do that. Okay, so let's zoom it. All right. Now in CST plot, we would like to scale the plot in order to have a fair comparison. So let's scale the plot as it is done in the reference paper. So minimum is -60 and maximum is -0. So that is the plot in CST, and that is the plot for the reference antenna. And you can see there is a sharp dip at 6 GHz, and also we have got the sharp dip around 6 GHz. Well, the plot is same. So our simulation is correct result. right? It matches with the reference paper. And then this is the first case where the theta and phi are both 0, the incidence angle. Now you will simulate the second case where the theta equals 60 degree and phi equals 0 degree. So let's simulate the second case. So let's save this file in another file, case 2. And this time the incidence angle theta value is 60 and phi value is 0. Okay, now we will change the plane wave setting because the incidence angle has changed. The theta has become 60 degree from 0 degree. So we will change the theta value here, 60, and press F7 button to update the parameter. Well, the plane wave looks like this. You can see the E field, the green arrow. It's theta-polarized wave, but the incidence angle has changed. Okay? Now we need to change some settings as well from post-processing template. So this was the first case, so now we will change some setting because theta value has changed. So make sure you update the value. Okay, and the rest of the values will remain same. Don't worry about the rest of the values. We only need to change the theta and phi value. Alright, now we will run this second case simulation. So the simulation will run and I will pause the video and come back when it's done. Okay, so this time there is no error. Did you notice? Because now CST knows which results are to be used for post-processing template. The error in the first case was very simple. So this is the RCS plot for the second case where the incidence angle is theta equals 60 and phi equals 0 degree. And we will again compare it with the reference paper plot. So let's scale this plot. Minimum is minus 65 and maximum is minus 10. And this is the plot for the reference paper, figure B. This is for the second case, if you remember, and this one, yeah, theta equals 60 and phi equals 0. This one. Okay, so as you can see, there is a sharp dip around 6 gigahertz, and then another dip at around 8 gigahertz, and then a peak around 12 or 11.5. Yeah, the curve is almost similar, 99% similar, right? So that means our simulation is correct. It matches with the reference paper. Great. Now we will verify the third case where we will change the polarization of the incidence plane wave. And this time we'll use a phi-polarized plane wave. Okay, this figure. And then we have to change the value of alpha because we are now using the phi-polarized wave. So for that, give a value of 90 degree. Then the theta will be 15. Now let's check the plane wave. Right, the E field direction has changed. And also the K vector, the propagation vector, the wave vector actually, you can see the direction and the theta value has changed, the incidence angle has changed, so K also changed. Okay, so we are now, we will also change the value of theta in post-processing template like we did in the previous time. So, well, before changing the post-processing template, I'd like to save the file as case 3, and this time phi-polarized wave. So I will write phi-pol, and the incidence angle is theta value 15 and phi is 0. Okay. And now we can change the post-processing template. Theta value will be 15. Okay. We can start the simulation. So this is the last case that I'd like to verify. I will pause the video. And this is the completed simulation of the last case. And this is the RCS versus frequency plot for a phi-polarized plane wave. This one. Yeah, figure B. This is the plot of the reference paper. And I would like to compare this plot with our simulated results. And I would like to rescale our plot. So let's rescale our plot in order to have a fair comparison. Let's define minimum as minus 70 and maximum as minus 10. Okay. So there is a sharp dip around 4.5 gigahertz and another wide dip around 9 gigahertz. So it's same. It's almost same, right? So this is for the theta equal 15 and phi equals 0 incidence angle. And alpha value is 19 because we are using phi-polarized wave. So in this video, we have learned how to find out the RCS of patch antenna, and we have verified our simulation results with a reference paper for 3 cases. And if you have any question and comment, please post it in the comment section, and you can download the CST file from this link. Thank you very much for watching this video.